Thank you, everyone. So, hi, everyone. Today I'm going to speak to you about what we're doing at Lagrange. I'm going to talk about a bit of SQL and more technically what we are doing behind the scenes. So, let's go about it. So, why do I mention SQL here? Basically, we are building a verifiable SQL VM. So that means you can query the database and get a proof and the results, that the result is correct. So how does it look concretely? Then, okay, it looks like this. Basically, we are focusing first on the historical blockchain data. So basically, if you have, for example, take a ERC20, so think about USDC, for example, where there can be millions of entries from the user address to the balances. Then you can actually register a SQL query where you say, give me the average balance of this user for the last 2 weeks. And for this address, you can use placeholder as well. And we're going to give back the results and the proof on chain. Okay, that's more like the product-facing point of view. And I'm going to explain to you how we are doing it during this talk. And I'm happy to talk more about the product side after my talk because it's going to be 50 minutes, so very short. Cool. So what do we do here? We are talking first about indexing historical blockchain data. So that means that every block, we're going to insert the values of some slot of interest in the contract. For example, if you have the mapping, we're going to insert all the mapping entries into our own database. Okay? That's called the indexing part. And we're going to do this at every block because we want to keep the values and want to do the average, for example, or over more complicated SQL queries down the line. Then comes the query part. Okay, so this first type is just insertion. Think of it as a time series database. And the second part is the querying part, where we actually run the SQL query across a subset of this database, and we prove the results. So what is our database? I've been mentioning this since the beginning, but we need a database which is, well, proof-friendly, okay, because we want to give a proof. So that means we can't use things like, it's not very nice for us to use things like Ketchak and RLP encoding for those who know how the MPT trees works on EVM. We want also to be horizontally scalable. Just to give you an order of magnitudes, if you want to do an average across a full week, just like on EVM, on L1, on Ethereum, it's like 50K blocks. If your mappings have, 1 million entries, you're already 50 billion entries. Okay, so we want to be horizontally scalable to be really handling large-scale computation. The third point we want is also efficiently updatable. That's a very, very important point for us. Imagine between block I and block I+1, there's only one swap of token. I sell some of token and give to another holder. Then I don't want to have to reprove the millions of entries for this block. I just want to efficiently update my database such that we only insert this new value for me and the recipients. Okay? So how does it work? Like I hinted before, at every block, we are looking at the storage slot of interest for some contracts. So for the variable mapping thing like this, we can do strict, we can use single variables thing like this. Later, we're also working on the transaction try, receipt try, and everything. And we are extracting this value, we're proving that all these values belong to this contract, and we are inserting the same values, but in a more ZK-friendly format, so no RLP, no Ketchak, thing like this, with a nice, think of it, of database as a nice BST Merkle tree with Poseidon. Okay, it's a fairly bit more involved than this, but I'm going to skip the detail for this talk. And we do this at every block. And so we insert all this value into our database. And then comes the query phase. Okay, so the query phase, here it's a very simple example where you can imagine you want just to compute the average. So you compute V1 plus V2 on the left node, on the left side, V3 plus V4 on the right side. You can compute this in parallel. So this is where the parallels property comes into before. And then you can aggregate the proof to get the final proof at the end. So here for the query phase, we use recursion as well a bit. I'm going to focus a little bit more on the indexing part because this is like really the crux of what we are building here. Let's skip this one. So how do we build this database? So we need two major ingredients there. First, we need what we call record trees, which is a paper invented by the research team Lagrange. So let's take the problem of we want to prove a membership proof for many leaves inside a tree. Okay, it could be a Merkle tree, it could be MPT tree. Let's take the naive approach. Okay, if we use a regular proof system like Groth16 or, for example, any ZKVM, the usual way you would do it is like you feed all the witnesses, so you feed the value 1, 2, 3, 4, and you directly prove that they all are inside this tree. Okay. what happens when we update the tree? So for example, from block I to block I+1, there is one value that changed. Let's say now instead of 3, it's 8, okay? Well, basically the path changed, okay, but the rest didn't change. But inside the proof, you still need to give all the values still. So the computation is linear in the number of entries here, because remember, we are appending things. So we are copying all the values from block I to block I+1 and only change the one that changed. Here, I still need to run a proof across all the values. So that's not good for us, because, again, think of a large-scale contract with millions of mappings entries. That's not scalable enough for us. So what we do instead is we go more into the MapReduce paradigm. Instead of doing one big proof over many data, we do many proof over a small set of data. So now we turn the thing around and we say one node of the tree is equal one proof. Okay, so we have one proof for the node 1, one proof for node 2, 3, and 4. Each proof exposes the hash of the subtree that is rooted at this node. Okay, so for example, in the left orange one, then we're going to have the hash of the concatenation of the hash of 1 and the hash of 2, okay? And so we're gonna have two proofs at the middle and one final proof for the roots. Here we use a lot recursion. You can see that the proof in the middle needs to verify the proof for 1 and verify the proof for 2. And the top group proof needs to verify the children proof as well, okay? So we use recursion all the way here. So we pay a bit more because recursion is not cheap. The nice thing about it, though, when we update, well, we don't need to recompute everything. Now we only need to recompute the proof from the value to the roots that change. Okay, so this slide is wrong, it should be 8 here. But imagine 3 is 8, then you just recompute the proof for 8, its parent and its parents. And here for the 4, you can just load it up from the previous block. You don't need to recompute it, just take the one that we had before, okay? And so that allows us to have a complexity logarithmically in terms of number of updates now. So our assumption is like the block entropy, the entropy between blocks is fairly low, so there's gonna be a few updates between few transfer between blocks, and so that allows us to be very fast in proving updates now. And so what we do is just copy the whole database, and we just recompute the proof that we need to recompute, and we leave it as it is. That's the first tool, okay? The second one is the digest translation. So this has been hinted already by Jens Grove this morning. We are also using multi-set hashing. So the problem here is in MPT, the order is complicated, let's say. It really depends on the key you're putting in the mapping, things like this. EVM and Solidity, there's very special rules. And so you don't have a nice structured order. For example, we could have the value 1, 4, 3, 2 in this order if you just enumerate the leaf like this. And we have very much different kind of branches and filling this and extension node and all this stuff. These are non-proof friendly at all. And also it imposes a certain order into it, okay? And we don't want this. We want to build a database which is efficient for querying. So that means we want indexes, we want a BST property as well, proven thing like this. So how can we turn this weird ordering into our own nice database? We can't just use a hash function because the order is important here. And this is where the multi-set hashing comes into place. So basically, it's as explained this morning, you just take your message, you hash it, and you map to a point in the group. For this, right now, we're using Plonky2, and we're using the EC-GFP5 curve. And so we do a hash2 curve on this curve, which is based on an extension field, the fifth extension field of Goldilocks. And we just compute the digest in the MPT. Okay, so we have digest D here. We compute the digest on our own database from the same value. So you can see D1 plus D2 plus D3 plus D4, this is the Merkle tree in order. The D2 is from the MPT, but then the result is the same. And so we, at the end, we recursively verify the true proof and to make sure that both have the same digest. And if both have the same digest, that means both contain the same data that we extracted. And that's the second tool. So basically, when we put things together, at each block, we are extracting the value of interest from the MPT, extracting the value of interest for our own DB. We show that they contain the same digest. We only update the proof that are needed during the update, right? And that's it. We do it at every block. Then now comes the query part of it. So I think I have this slide. So the query part of it is fairly short because of this talk is quite short. But basically, we treat each node of the tree as a logical SQL row. So think of it, each node can contain your balance, the total balance, and the user address, for example. How we going to do the query? Well, our tree is kind of a BST tree, so we're going to look right in the portion that satisfy the predicates on the index. So for example, if we had an index on the address, then we're going to sort the tree, we have a BST tree on the addresses. And so we're going to look at all the rows that satisfy the predicates, we're going to show in circuits that they satisfy the predicates, and we're going to compute the results. And then we simply go up the tree and accumulate the results one by one, okay? So at the end, when we reach the top of the tree, we got the aggregated proof, aggregated results, and we can just submit this on chain. And we, of course, we do a wrapping gross-sifting off chain to submit on EVM chains. That's our main target right now. Went a bit fast. Okay, got 5 minutes. So the other thing I want to quickly mention to you today is also the fact that, as you saw, we are using recursion a lot. So that means we are generating a lot of proof. Like I'm talking about 200, 300, 400 proof per minute easily. So we're dealing with thousands and thousands of proof. To generate all this proof in parallel, we need a strong proven network. So we're also building our own proven network, basically. So we're building the proven network and the application building of it, so dogfooding. And so here it also requires quite a lot of changes. So we are an AVS with restakes security from EigenLayer. So here the economical security only comes for the liveness property. So if I send a task to a prover and it doesn't reply me with a proof in certain timeout, before a certain timeout, then it's going to be penalized. But the guarantee that the proof offer is still relying purely on the cryptography assumptions. The stake is only there for the liveness issue. And yeah, that's really basically the other side of Lagrange, also what we are building. Again, the proof network and the application building on top of it. Just a final quick slide to just show where we are right now. We we shipped on April the Euclid testnet with a basic side of query where we can only extract mappings. We implemented the proven network in May. And we just recently launched our ZK processor 1.0, where we have the basic of the SQL VM now fully implemented. And now it's just a matter for us to implement more and more SQL functions. For example, we're going to be working on joins, order by, group by, all these things. Simple select. And also more and more data that we want to extract. We want to extract the receipt tries and the transaction try as well. And then coming up for ZK processor 2, this is when all the features will be there. And I guess that's about it for me. I have 2 minutes for question if there is any questions.
Do we have any quick questions? We have 2 minutes. Over there.
Sorry, great presentation. Can you do zero gas transactions with Lagrange?
Can we do zero gas transaction?
Yeah, what was the cost usually for a query?
Okay, so right now the cost first is to verifying a gross-sifting proof on chain. So it's like 280 gas or something, 200 gas, depends on which type of gross-sifting we're using. And there's also the cost of querying. So for example, if you are querying a month-long average or a week-long average, if this is 50K blocks, for example, for a week-long, if you're only querying for 2 hours, if it's 600 blocks, so it's not the same range of computation as well. So also the price model is to be determined as well according to the size of your query. And there's also the part, this is for the query part, there's also the indexing part because we automatically index some tables. So we need to also to take that into account that we are, at every block we are automatically making some proof. So we are doing also some work there. So there's also we have to pay for the indexing and for the query. But the cost there is not that significant if we can use our proven network efficiently, and so because we are not paying the cost of proving them directly.
Okay, that's all. Oh, wait. Is it a fast question? It's ZK, it's not good.
Thanks for the presentation. The values that you're storing in these record trees are like usually public values or like a representation of like the storage of a smart contract on chain, or they can be also private values?
Yeah, so here I presented our main use cases, which is on-chain historical data, but again, we are building a verifiable SQL VM, so we could put any data into our SQL. The nice thing about blockchain is we can prove that we correctly extracted this value from this contract, from this cloud storage, from these variables, from this block header, with this chain ID even. We can be cross-chain compatible and everything like this. But we can totally also upload just NFT metadata, which are not proven at all, and we just put a hash as a kind of commitment, and that's about it. But we can't, the client will have to trust that it's done correctly, because we can't prove it's come from. Thanks.
Okay, thank you, Nikkolas. Round of applause. And